So ladies and gentlemen, welcome. My name is Armagan Al-Haq. I'm the Manager of Program Development and Partnerships at Waterloo Institute for Sustainable Energy at University of Waterloo. I welcome all of you. Thank you so much for joining us. I would like to introduce our today's speaker, Dr. Mahdi Shahbakhti. He is an Associate Professor of Mechanical Engineering at Michigan Technological University, where he conducts research in the area of controls and energy systems. Prior to joining Michigan Tech in 2012, he was a postdoc scholar at the University of California, Berkeley for 2 years. He received his PhD in mechanical engineering from the University of Alberta in Canada in the year of 2009. An American, if I'm not mistaken, it's an American Society of Mechanical Engineering and Society of Automotive Engineering member.
Correct, yeah.
Dr. Shahbakhti has been doing research in the area of controls, powertrains, and energy systems for the past 17 years. His research centers on developing dynamical models and novel control techniques with applications in vehicles and building energy systems. He is the author of over 120 refereed publications in the field of powertrain, energy systems, and controls. Ladies and gentlemen, please put your hands together for Dr. Mahdi Shahbakhti.
Yeah, thank you. Thanks for the introduction. Good morning, everyone. How are you today? Yeah, so thanks for coming to the talk. So what I put together about the materials that we have been doing the research in the past 5 years that I have been across the border in US. And what I will be talking is about how we can see the energy systems. Energy systems are broad. They can be any types. My focus would be on the automotive energy systems and the energy system that will be used in the buildings. So we can see how, if we learn about the dynamics and we can kind of understand that dynamics, how then we can apply control techniques, and as a result of that one, we can try to save energy. That's basically the focus of the talk. So the topic, a little bit, I will give a little bit background about myself and Michigan Tech, because I'm not sure if all of you are familiar with Michigan Tech. And then the focus, one part would be on the building energy systems, and then automotive energy systems. They are very different energy systems. If you look at buildings, the time scale of them is much longer than the automotive energy systems. For example, in internal combustion engines, things can happen in the order of the millisecond. Whereas in this building, say in this room, the temperature can change in the order of the second. So they have very different dynamics in terms of how fast they would be. And also there is a big change between them, big difference between them. If you look at the automotive systems, for example, you go and you buy a car from Toyota, GM, or any other companies, they make millions of those same systems. For example, they might be using the same internal combustion engines, the battery system in many of their products. So the plant, or what we have, is kind of fixed in that sense. Whereas when you look at the buildings, there is a huge variability. If you look at this building compared to the next, and even the functionality of this building, today is a seminar room here, another day might be a classroom, or it might be a workshop. So the dynamics will be all different. So these are very different types. So in that sense, for the building energy system, coming up with the models that would be variable from one system to the other will become challenging. Whereas for automotive energy systems, you can do a lot of extensive testing. That's what the automotive OEMs, they do. So then you can use them, and then so you can get that luxury. But for buildings, it doesn't make sense. I spent several years to model how this room is going to be performing. And then suddenly, the people will decide to change this room, so totally it will change. So those are the big differences between these two systems. So let's have a brief overview of the Michigan Tech. So this is where Michigan Tech is located. So Canada is here. So here is the Lake Superior. So we are located here. We're pretty much north of Michigan. The school has about 7,000 students. It's mostly engineering and science. Mechanical engineering program is a large program. The program that I am from has been sitting in the top 15 in terms of size in the past, 50 plus years. So it's about 1,395 undergraduate and slightly over 360 graduate students. And this is how it will look like in winter. So you can guess what this is located here. This is a river, so it's all frozen. And then we get lots of snow. And then guess how much snow we get in Michigan Tech or Upper Peninsula. I check in the morning how much snow you get in Waterloo, and the average was about 160 centimeters of snow, and we get about 5.3 meters of snow. So it's a place that we can have lots of fun with snow. And then actually university has a ski hill, so students can try the ski for free in day one. This is another one if you came to visit us in winter. So we have a winter carnival. So students will go and then burn statues. I think there will be a lot of thermal engineering management need to be done because some of the statues need to be built over the night. So that was a winner for this 2017. So that's a little bit about the Michigan Tech. About myself, I have a background basically in 3 areas. One of them is area of the controls. And then the other one is energy thermofluids. And then the other part's experimentation. So what I typically do that I try to have understanding of the thermofluid system. So when I understand the dynamics, and then I apply control, and then finally I use experimentation to show it works. That's how it's been about me. So generally I can call it under the umbrella of energy mechatronics because we use a lot of electronics to implement them. So when I joined Michigan Tech, the lab I established is called energy mechatronics. And as you heard also in the introduction, is mostly focusing of trying to increase the efficiency of the energy system by applying advanced control techniques. There are 5 areas that my lab has been working, Michigan Tech. A good portion of them all collaborative works. You will see the name of the collaborators. One of them is the area of the building energy control, mostly focusing on the HVAC, heating, ventilation, air conditioning. That's the main dispatchable load in buildings, and that's the part that you can have a good control on it. The other area is that when you integrate the buildings to the power grid, so there would be opportunities as I will be talking about. That's on the building side, and then working in the area of advanced IC engines, how to control them to maximize efficiency, hybrid electric vehicles, and finally the connected and automated vehicles. These are the 5 areas that have students working in the area. Generally, these 2 areas can be more categorized as a smart city or a smart community, if you have heard that area. And what actually the students will do all the work. So these are the students that we have had in lab. Some of them already graduated, and some of them are started, or some of them have seen the program, so they are working through. So they will be working in different areas, and then we will be working with them. So this is the acknowledgement to all the past students and all the students who are working, because what I'm presenting is belongs to the works that they have done. So that was a brief introduction about Michigan Tech and myself. So now let's move on to the topic of the building energy system. So I will talk about 3 areas, again, because I'm trying to cover a good portion, so it would be more on the high levels, but I would be happy to provide, there's lots of publication in different areas that I will be happy to share it with you. So on the building energy system, I will start talking about the modeling first, and then later how to do predictive control, and finally building to grid integration. So one of the nice things about the research in the building area is that a lot of buildings, especially new buildings, they have a lot of temperature, humidity, and some of them CO2. So we have lots of sensors that they can be generating a lot of information. And that we can use it to develop a model for a building. So it's a little bit different compared to my research area in automotive that is very expensive to put a lab together. But here, you could collect a lot of data from the system. So this is an example. So we get these data from the different buildings, and then we try to develop a model, and we can easily verify those models because we can see how the temperature or the humidity is changing in each room. So here's an example of the office building that we'll look at it, and we add more sensors to it as well. So here, what we have here, this was using a ground source heat pump. So it's a geothermal. It's using the energy from the ground. And then, as you expect, Michigan, the area should be cold. So using the air source heat pump will not be a good idea. So we use the geothermal, the energy from the ground, and then later you will have another heat pump that it will heat basically through the air handling units. So there's an air handling unit here, and that will go finally to another secondary heat pump here that it will heat the air that's going to the room. So that's an example of the systems that we have. And another good thing on the campus is that you got all different buildings with different nature. So what we do is that we look at the schematic of the dimension of the buildings, and then from there we kind of start developing a model. And then the models that we have been using has been mostly because we wanted to use it for control. So we'll be limited how much we can incorporate. There are a lot of models that can be, especially for transient, they can become high fidelity, but then when we want to implement it, would be more limited. So the first approach we look at it, which is a very common approach, is that you will kind of model the different parts of the building with the approaches known as the RC model, R for resistance and C for capacitance. So what you will do is that if I go next slide, so this is I can use the same slide actually in the course thermodynamics that I sometimes teach. So it's the same thing that they learn in that course and also related to heat transfer. So you will see that what's the change of the energy of the room, and then as a function of the different dynamics happening. So you will include the conduction, convection, and the radiation. And then if I'm looking at the energy balance of a room, so you will write it, the sum of the parts is that how the room is changing, how much would be the thermal energy storage. CP is like a specific heat for thermal storage of the building, and this is for the radiation term, and this is for the internal energy. So when you put them all, then we have all the terms there. So we got the major dynamics is captured over there. And then we verify the model. This is an example of the model, and it works nicely. And then we said, OK, it seems good. And then what will happen, we notice that, oh, my goodness, we have not included many of the disturbances that might happen. Or depends how I'm doing those modeling. For example, when I'm looking at the convection, it will be depending on the H, that's a convective heat transfer coefficient. And at the end, that depends if it's going to be a windy day or if it's not going to be a windy day. That's changed. And if I want to develop a model that it can capture all those dynamics, then it will become very complicated. If I have one day, last night you have a thunderstorm, I brought an umbrella, then that would be a different day than the other. So if I want to capture all these and trying to predict them, it would become very complicated. So in the work that we did, that was a collaborative work with the University of California, Berkeley, is that saying that how about we go based on that baseline model, saying that RC model, and then we make the model adaptive. Based on the inputs and the output, the measurements that will happen, we will make it a parameter adaptive model. So the baseline model will stay as linear as possible, and then but we will let those parameters to become time varying. So we use the data from the buildings that are collected and goes to the one offline one-step calibration, and finally go into the Kalman filter estimation. And then what we did, so this would be a period of time that it will not work, and because it would be on training, and then finally it's going to start becoming more accurate. When we talk with the people from the building energy industry, and they all say that, yep, if you can give me a very nice model that it captures all those dynamics, I'm willing to put the the more capable controller to save energy of the building. But then they tell you that, please don't tell me I need to spend 2 years to develop a model for just one building. So that's the challenging part. So this is the major part, that commissioning of the building energy. So in this way, what will happen is that we will develop that model, and the models can actually become self-learning, heap learning. And then we will use that one for controls. Then the other works that now, because of the renewable possibility, and especially for buildings, this is the PV panels that we use in the Kivina Research Center, that's the research center we have there. So they tested different PV panels. We got the data, and then finally we developed a model that it can tell us that for different operating conditions, how much would be the electricity can be generated by PV panels. PV stands for photovoltaic. And then what you can see here is the cell temperature of the panel, and then this is the irradiation. This should have been a nice sunny day because this is the time so that during the day you got this. It's not always like that, especially when you become more cloudy. You are not going to get such a nice radiation. It tells what would be the current of the panel, what's the voltage, and then finally we can say how much is the power measured and how much power was predicted. So we developed a model that it can tell us for different operating conditions how much would be the power you can get from the PV panel, because we want to use that one as a renewable energy integration with the building. Then I want to talk a little bit about one of the concepts that some of you might be familiar, but some may not be completely familiar. How many of you have heard the term Exergy? Okay, about 40% of you in the room. So that's the topic that will be in the thermodynamics that they discuss it here. So let me briefly talk about energy versus exergy, and then I can tell you how it can be useful when we do the building energy control. So what we have here for energy, you always learn about the first law of thermodynamics. This, if I'm looking at this room, the temperature is changing, how much is the saying cold air is coming, and how much heat is generated by us, and then how much is leaving. As a result, I can say that's the energy balance. And that's all about the first law. But when we look at the second law, it can tell us more about what are the sources of irreversibility. For example, if we are losing, if the fan coming here, the air is coming and the mixing, so we have those irreversibilities. But the key is that those irreversibilities are the sources of deficiency. So typically what we see in engineering work, especially in the control community, their models are mostly energy-based. Exergy is used a lot for the people that they do analysis or design, but control community, they don't do much as compared to the others. There are people working in the Exergy control, but their numbers are much smaller compared to them. So let's have one example to explain why Exergy would be a better way to understand. So this is a cup, and so I ask my students, so we put the cup, and this is inside is hot water. And then we calculated how much energy this one has. So what we have here is saying that if this was saying the water was inside here with the temperature, we calculated there is 42 kilojoule of energy. And then we see how much work we can get if you calculate, if you go to thermodynamics, you can see how we calculate Exergy. Because Exergy will tell you how much is the availability of the work. From that amount of energy, how much work can be extracted. That's what we mean by Exergy. So when we do Exergy, we said, OK, it's only 5 kilojoule. And they said, OK, so let's put a Stirling engine on the top. This is a Stirling engine that I use sometimes for demo. And then see, nothing happens. So the energy was not enough to start turning that Stirling engine. And then we said, OK, so let's put some ice. And then we put some ice on the top. So what happens, the energy over here, did that energy change? The energy that we have inside the cup. It did not change. If it was the hot water at the temperature of 100 degrees C, that energy was the same as before. But now it's turning this, so it's working. So there should be something else that I'm missing it when I'm just looking at from the energy perspective. So and the key is the Exergy, because Exergy will be also depending on the environment that we will be calculating. And so here we can get 18 kilojoules, so then that was enough for this case to run it over here. So generally, Exergy will make it a better metric when you are dealing with energy system, especially if you want to minimize energy consumption. So I will show you with the example of the building later. So what we did, we said, OK, so let's convert all the models we have, which was the energy base, and then we convert them all becoming Exergy. And then so the framework become Exergy. And what we will do, we will try to minimize Exergy destruction. That's what, because Exergy is telling that how much good work you can get out of the system. So we don't want to destroy it. So then this would be the Exergy destruction. So first term is for the heat transfer, the second term for the Exergy flow to the system, and the third part is that when the Exergy of the system is changing. And then there are thermodynamics equations that you can use to calculate how much would be the Exergy terms. And then finally, we form the differential equation that it will tell us how much would be Exergy destruction. So one thing we will do is that what we will try to do in our controls, we try to get to the targets we want, but we try to minimize Exergy destruction. saying that we know here would be 8 a.m. There's a classroom. So we need the temperature here to be, saying, 20 degrees to 24 degrees C. So that's the requirement. So we always meet that requirement. And then we try to see how we can do it while the exergy destruction will become minimized. So we apply the same concept for HVAC control. And we also did the same for IC engine control, again, for 2 separate. And then we could see that how saving will happen. So after we form all the models, we learn about the buildings part, renewables that we have that part, and then this exergy part. So then we form them in a differential equation. So here we are having the disturbances we have. We have radiation, we have the internal heat, and we have the outside temperature changing. So this is what we could use in control. We call it state equations. The X here can be the room temperature, U can be the control input. And then we discretize the dynamics of the system. And then for this case, U control input, we use the supply air temperature. So these are the fans, the air is coming. So then same, we are controlling that temperature. We did some other works that we controlling both temperature and the flow rate. So that's the other work. And then the states are basically the neighboring zone's temperature, and the output was the temperature that we wanted to control. So that was all about the modeling part. Because again, the key is that if we develop proper models, we can understand the dynamics part of it. So that's conclude the first part of the building energy system. Now let's use that knowledge and try to control the system. So typically, what happens in the HVAC industry, this is very common, that they use a PID and is mostly on and off controller. And they are very effective controller, and they work nicely with the low cost, but there is one limitation for these controller, and that's there is no integration of the system dynamics, because they will act upon what is happening right now. And also you cannot include a lot of predictive information, because control doesn't do magic, it needs information. So if you give good predictive information, what's going to come next, so then that information can be used in the structure of the control, so then we will become wiser when we are doing the controls. So that's the limitation of what is used in the industry. But these can also become very effective if you learn from the optimal control and then modify a lot of control logics that is used. So the approach that we have here, we use the model predictive control. That's approach for model predictive control for HVAC systems has been used for years. So that was not any new part there. So what we used here, just for the people who are not familiar, is that we will see that how the building energy, saying the HVAC load, is going to change versus time. Because we know there's a classroom here at 8 and 10, and the people will go also. Then you kind of predict what would be the energy consumption need for these energy systems over here. And then here we develop a model. So this part was the more new compared to what's in the literature, saying that the Exergy model of the system, and we also did the energy model as well because we want to compare. And then you will see what is the desired temperature. You usually have a bound coming from the ASHRAE standard. And then you control the MPC controller. You also know what are the constraints you have. For example, if I have an actuator, I cannot get the flow rate here becomes super high. I cannot get, if the temperature was cold, I cannot get the -5 degree coming out of that. So a lot of actuator constraint you could there. And then with that, you control the inputs to the system, saying if this was a heat pump, so I will be providing the input to the system. So again, yeah, you have a measured input and then predicted exergy and energy consumption. So what we did, we're comparing it with typical rule-based control, energy-based control, and exergy-based control. So in model predictive control, you usually have a cost function. So you form a cost function. We are trying to minimize this term over here. What is that term? It's the IE, energy index, for the power for cooling, power for heating, and the power for the fan. We always need to have a minimum flow rate because of the ventilation. So there would be always the power of the fan. And then you have a system equation. You saw all the equation I showed you in the part 1. So those will come here and then become like an equality constraint. So those are explaining the system dynamics. And then some others for the control inputs, actuator dynamics, and then some other terms that we wanted to make sure that we will get the feasible solution. And then this was for energy-based. And exergy-based, we try to minimize the exergy destruction. That was the main goal. That's what we wanted to do. And then we have the same constraint for the inputs that we can use here. In the rule base, typically what it does, when the temperature goes above certain limit, then it's going to turn we need cooling, it's going to turn the cooling on. If it goes below, then it's going to turn it on. And usually they also put a buffer, so it will not become on and off, so it will become noisy here. So now we can compare the results. So A is showing the rule-based control. I'm showing it at RBC. So here what we have is the temperature, and here is the time. So here is the temperature bound. It's typically coming from the ASHRAE. You can modify those. And so this is the room temperature. So for this, and this is the supply air temperature that is coming. So for here, as soon as the temperature is violated, then heating will become on. So it's going to heat the room. And then later, we are within the bound, it's not doing anything. And then as soon as you are going down, it's going to heat it again. So that's typical rule base. You can make it more and more complicated if you want. In the model predictive control, what it does is that saying, OK, I'm going to start heating the room earlier. You see this one is starting here, is, say, I don't know, 3 a.m. So I'm going to start it earlier. And then the room will be adjusting, will be always within here. And then what will happen, my room temperature, it will be always on the lowest bound. So if it's always on that lowest bound that I'm allowed, so my energy consumption will become less. But what was the magic here? This model predictive controller knows what's the system dynamics. It knows that, OK, if I'm going to give this much heat, how the system dynamic is going to change, how the temperature is going to change. So because it has that knowledge, then it used it and then did that the control. So this was the energy-based one. And this is the case that when we use Exergy one. So for Exergy, it's actually start heating it over here. Typically for Exergy, when you have a big change of temperature, that will cause destruction. So what it does, it tries to minimize the variation of the temperature. So the peak temperature that it will be using for supply, it will become less compared to the energy base. And that will translate to the minimal Exergy destruction. And because now Exergy destruction means trying to minimize energy consumption. So with that, this is how we get. Yes, it stays still on that, but here it keeps the temperature of the room such that we will be having a total energy consumption less than that here. Here we see the Exergy destruction, the blue one, what is happening. You can see when the temperature of the room goes up, then we will have more Exergy destruction. And this one is showing how much is the cumulative Exergy destruction. So we can compare between the rule-based, energy-based, and Exergy-based. So here is the table that for the works we published in Journal of Applied Energy 2015. What we see here, this is the Exergy-based, this is energy-based, this is rule-based. So here we can see how much was the reduction of the Exergy destruction compared to the rule-based. How much was the reduction of the energy consumption. So when we were using the energy-based MPC, we could save 24% of energy. And then when we were using the Exergy, we could go further because we had, our cost function has more knowledge of the system compared to the energy. That's kind of. So this basically, as you saw here, it concludes the second part of the building energy. Now we go to the third, because you can keep improving it. But it should be on the good grounds that you know your system dynamics and are correct. The next stage is that, how about these buildings are actually connected to the power grid? What would be the opportunities there we can do? I don't know how many of you have seen this graph. This is known as a dot curve. 1 person, okay. 2 persons, okay. I had a discussion if this is really look like a dot, but yeah. So this is from the information from California. So what you see here is this is a megawatt for the power, and then here is the different times of the day. So what we have here, this is based on the actual data. This is 2012, this is 2013, and this is how the predictions when we go further. What is happening now, the power grid is changing because now with a lot of incentives and a lot of opportunities, there's a lot of renewable energy that can come to the grid. Especially the PV panel during this time of the day, you saw we got that peak of radiation. So now what will happen, there would be a lot of power generation by the PV panels or other renewable energy sources. So as a result, what will happen, we will have these with the demand for the power will become less because I'm generating enough power, I don't need to use the power grid. So this shape is changing what will happen here. But I do collaboration with my colleagues in the Department of Electrical Engineering on the power grid side. And then for them, when we talk, They prefer this one to be flat. We have a term, we called it, for example, load factor, that we don't want big surprises. We don't want the big ramp or big going down here, because it will bring more cost to the power grid. So now this will cause problem because the power grid has not been designed to be working with such a big changes. And also later, when all the people's coming back home and it's also becoming dark, there's not much more renewables, so then you need a lot of powers going on. So that becomes the challenges that we have because of the renewables. And renewables also, another problem is that they are not as predictable as you would like to be. For example, for the PV, if it's sunny. So now we can see what can we do with what we learned from the building energy control to help the power grid, and maybe that it can help us to incentivize, provide us some incentive. Maybe we can reduce our electricity price if you cooperate with the building. Because if I can adjust the energy that for the parts that I have control, first maybe for the lights I will not have control, but for the HVAC control I have flexibility, and that's for the buildings, depending on where you are, is average about 40% of the energy in the building for the HVAC. And then, so what will happen is to see how much we can help to flatten this demand. So the grid will give me, this is the demand I have. Can you help me to get reduce your demand here or increase your demand at this time? So I can work with the grid because I know my system dynamics, and I can make sure that the people in the room will not become unhappy, but at the same time I'm providing the services over here. And then later, when I have this peak, how much of that power, if I have a special energy storage, I can use it for that purpose. So I have some brief slide in this area of research we do. So we have information about the buildings on the campus for energy consumption. So what we have, you saw the building energy model that we had. We had the renewable energy based on the experimental data, and we also have the battery based on the experimental data that did not present here. And then here it tells how much is the power that is generated by the PV. And then what I will do here, I will decide how much was power coming from the power grid, so from the grid to the building, and from the grid to the storage system, and then how much of that power from the renewables goes to the building. P power for the PV, and then here is storage to the building. So this was the collaborative work that we were working with the electrical engineering with the Professor Sumit Paidawal. He was actually a Waterloo graduate. He did his PhD at Waterloo. And so what happened here with developing a model for the dynamics of the grid, and also the thermal and building energy side. So we could decide how much it would be the optimum for the power from the storage going to the building, how much power is the building's demand can be adjusted, and then at the same time, a state of the charge of the battery, saying that in this case for comparison, we wanted to keep it almost constant. So you can see the system is becoming more and more complex, and your optimization has more variables, because I got now renewables, I got the energy storage that it has its own charging, discharging characteristic, and I got the building thermodynamics, and I also got the grid, which is serving different buildings. So now how we can try to optimize the whole system. So we use the knowledge of the buildings that we have. So on our side, it was a building to grid. It's a B2G bi-directional optimization. We were doing it on the building side, saying on the model predictive control, and then he was doing it on the electric side. So these two will communicate. So what we make sure on the building side, when we have the temperature control, the temperature always stay on the lowest bound. So we are not making people unhappy. And as a result of that, we will also make sure that what has been given to us for the maximum load from the building, we will try to, we will try to basically always stay below what's the limit, because you don't want to have a power outage in the grid. And also the load rate, ramp rate. You saw that one. We said we don't want to have a steep changes. So what happens, I know how can I adjust the load of the building to the extent that is not making people unhappy. Of course, I will not be able to accommodate anything because it depends on what's the current state, but at least I can use my knowledge to help the grid as much as we can over here. So in this case, we could accomplish to staying within the bound that it was allowed by the grid. And the other one was when the grid, this is known as a demand response in the power grid. So this is a DR signal, demand response, coming from the grid saying that, can you do me a favor during this time, have your load following this? because it will help me for the grid side. And then we go on the building control side. You can see the supply area is controlled such that so we can get to the what grid has been asking us here. So this is a very active area in the building to the power grid and is keep growing. And what we envision is already some states in the US have programs that it will give you incentive to participate in the demand response. So there will become a monetary value for the saving for the building as well. Then, as you expect, in all these simulations, they are specific to some situation. So what we did a Monte Carlo simulation because you can have all different kind of weather conditions, the temperature condition, if it's going to be winter, it's going to be spring, so it would be all variation. So after doing all those simulations, we presented what would be the probability of the saving here. So what we see here, this is the probability density function. Here is the cumulative density function. So here we are showing the potential for cost saving because you know the price of electricity is different during time of the day. So then if I use the electricity during the time that is cheap, and then I used it, then I will use it when it's less expensive, so then I can save money here. So the way we can read this plot is that they're saying that for, if I'm looking at this cumulative CDF, so for 50% of the cases we see the simulation, there was a potential for about, say, 22% of the cost saving. And then it was changing, varying depending on situation from, say, 42% to 5%, depending on situation. For the ramp reduction, to reduce it so we can see that how much would be the potential of that reduction. You can see there's a big variation because it would be depending on the scenario that the building is. And then the same for the ramp down reduction. So results actually recently published in the Applied Energy. Okay, with that, I summarized the building part. So we talked that with the model-based control, after you understand dynamics of the system, there would be a lot of opportunities that comes. We talk about the buildings model need to be adaptive, so they can capture dynamics. And we showed some cases that if you show Exergy destruction as a cost function and then you develop a proper model, we can save 36%. Again, this would be on that scenarios we do. It can have the variations on the conditions. And then finally, a lot of opportunities for the building to grid when these, because the main load in the power grid is buildings. Over 70% of electricity consumptions in power grid is consumed by buildings. So when these two work together, that can, we saw the potential for electricity cost reduction. That was the range we saw. And for the ramp rate was 5 to 32, 70%. So this concludes when we talk about we have the models of the system, dynamics of the system, and how we apply control. So that was the building side. So now let's have some highlights on the automotive sides. So I will go briefly about 3 topics. One of them is the internal combustion engines, when you have more advanced internal combustion engines. And internal combustion engines, the application is so broad. It's not just automotive. It will be used when a lot of utilities that they use in the tanks. So there's a very broad application for that. So one was that when we're using the advanced type of combustion regimes, how can we control them? And then we talk about the hybrid electric vehicle, and finally I conclude with brief notes on the connected and automated vehicles. So this is a type of, I'm not sure how many people here are from the automotive background. Okay, so about 40% of the time. So I go very high level. So here is a typical spark ignition engine, like a gasoline engines. You see you have a spark, and then it will create a flame, and it goes all the way to these regions. There are more advanced type of combustion regimes, and don't go into too much detail. This is one of the most recent one, reactivity control compression ignition. So you have 2 fuels. So each of them has different reactivity. And then with that, you can have a different gradients of reactivity. And that can help you to do a better control. So they have some of the highest reported indicated thermal efficiency for any IC engines that we can see here. So they have one of the highest. Some of the peak values for indicated thermal was 53%. And they have very low NOx and PM emissions. So they are very attractive. But one of the issues with them is that the operating region is limited. And also, when you want to operate them at the optimum, you need, again, to understand what are the system dynamics. So then you can control them. So that's the beauty of the control to me, that as soon as you understand your system dynamics, you can formulate it in the way you can, controlling and then trying to work it here. So what we did here, we developed our own lab. These are definitely much more expensive labs than the building side. Building was easier, we could leverage a lot. So this was the setup that we developed basically pretty much from the scratch, developing all the control units. So we could control 2 different fuels that it was injecting. We can control the octane number of that one and also what goes to the cylinders. And then all other control features. This was the pictures of the test cell. So basically, we could, for any control variables that we saw is important for engines, we could control. I don't go to the details because it might be off the topic for this audience. And then after we have our own experimental setup and collecting all the data, we develop a phenomenological type of model for that combustion. So what was happening here, we have 2 fuels that is injecting. So as a result, how much of this fuel compared to the other one, it will create gradient. And then we have a type of combustion, we call it a stage combustion, because you have when it's more reactive, then it's going to have autoignition. When it's less reactive, it's going to need, for example, higher temperature to autoignite. So we had that gradients. So then we developed a phenomenological type of model that's just coming based on understanding of the thermophysics of the system. And then we developed that one to say, okay, when is the combustion is going to happen in these systems? And then from there, we developed a dynamic model because that was a static model. Dynamic saying that the relation between the previous cycle to the next cycle. There are dynamics in the engines like residual gas dynamics, airflow dynamics, rotational dynamics, fuel flow dynamics. So we incorporated all those so then we can make sure the models would be dynamics. Then after that, we developed the states of the system. So previously, we saw building, which was the temperature, and if it was ventilation, it would be also humidity. Here, again, we have a state equation, or a state equation would be here, like here is combustion phasing, the temperature of a start of combustion, pressure at start of combustion, residual gas temperature, and mass of the cylinder at the exhaust valve close. And we use different control. How much would be the ratio of these 2 fuels? What would be the injection timing of fuel? And how much would be the fuel quantity of these 2 fuels together? And we have some different disturbances. And finally, we developed our own control logic. Again, it was same time, but just the dynamics are much faster here. Things are in the order of the millisecond. So then you can imagine I got luxury in the building side when I'm doing a model predictive control, which is computationally expensive. I have there a lot of luxury in terms of times, but here, no, it should be happening in the order of the milliseconds that I want to have here. Although if this was a formula car, then I probably have a fraction of the millisecond to do it because they have higher RPMs in the formula car. So we developed a model-based controller, and as a result of that, we have a Kalman filter here that it was for some of the states we could not measure, and then we could control all the 3 inputs to the system. As a result of this, I will control the combustion phasing to be the optimum I need because that will give me the best efficiency I wanted, and also getting to the load we want. These are some experimental results. So in the engine control community, this is representing the engine load. What it means, for example, if you are driving going up the hills, you press more gas pedal, that means the load will go up. So that means you are, for example, you're going up the hill. And then you have more power demand, and then what will happening here, we want to get it to the power demand the person wants, but at the same time, controlling the combustion phasing here to be such that is at the optimum operating range. So we are using different controls to make sure during while we are giving to the driver what it needs, but at the same time, because of this metric, it's going to be staying optimum, so then the fuel consumption will become minimized. So that was the kind of idea. So this is kind of summary. Typically what we do, I didn't explain here, that's a lot of collaborative work that what will happen here. So we'll do collaboration with the people that they do CFD and optical engine studies. So from there, we understand the physics. Again, the key is that we need to understand the physics, so then we can incorporate them into the dynamics model of the system, and then I can go to the control. So the success would be much more if I have more understanding of systems and then going into here. There are other type of control. It can be just based on the data mining. That's a different type. But I think our success has been mostly trying to understand the physics and then going from there. So we start from there. We develop saying the phenomenological type of model. then dynamic model, and then from there you design a model-based controller, and then finally you implement it on the testbed to show the results here. So the second piece that's on the automotive framework to talk about, that would be about the hybrid electric vehicles. Again, just the system equations are changing, but we are applying the same approach. So making connection to what we talk about, the engine part. So typically, you can have different regimes of combustions on the engine. This is a spark ignition, this is RCCI we talk, and this is another type here. And the optimum efficiency port here is showing the brake-specific fuel consumption. So when we have the values becoming lower, it means fuel consumption is less. So this region that is this color means it's pretty good. But sometimes you will have regions in different operating region that different map that it will be effective. So here for this case, this part the best for RCCI, this part the best for the HCCI. But then how about we have a multi-mode operation, multi-mode engine? It can operate in all these systems, and then you need to have transitions between all these things. So you will do the transition whenever it makes sense to minimize the fuel consumption. And then how about on the top of all these, we also have electrification. It gives me the maximum efficiency I can get because I can shave a lot of those transients that they are costing me a lot of fuels. I can get rid of them. It gives me flexibility to be on the best optimum I can so I can see how much we can save energy. Because especially in the automotive industry, they say that the total energy consumption is all about the sigma of the delta I. Delta I are a small saving. So if all the saving is small, it matters at the end of the total fuel consumption. So what we did, we developed, this is the AC dynamometer engine. So AC dynamometer, one side we have the engine and developed the same part for the electric motor, so for the powertrain. And then we could control it, we use a DSpace product, so we could control both engine and the electric motor on the other side. So this is the pictures of the setup, so we can control. So in this engine side, we could control all different modes. So the engine is operating in multi-mode with the advanced controls we do. On the left side, we do the electric motor, and then here is the battery set that we will be using, we used here. And then we could do all different torque blending strategies that we wanted over here. So what happens from all the information we got from here, we developed and we verified or modeled, and then we put them into the optimization framework. So this is just an example of one of the optimization frameworks. So we developed a model. It's just an example of the parallel one. So what happens, it was to focus on the supervisory controller to decide how much will be power we need from the electric motor and how much power we need from the engine. So this is for an architecture of the parallel, but there are all different architectures that we can. As soon as I have the components that are experimentally validated, then I can move on to the optimization. So again, becomes the same. We have a cost function. Now the cost functions become different. And then the state equation, which is representing the dynamics, are becoming different, and then I can apply them here. So what we have here is for this cost function, we are trying to minimize m dot of f, which is the fuel consumption. And then we will put penalty when the engine become on and off, because anytime that is starting the engine, there would be fuel penalty associated with that. And also we put the fuel penalty when you have mode switching. You saw there are different combustion modes. We have penalty for that one there. And then finally, for the gear shifting, this also would be another penalty. And then we include the constraint for, this was the state of the charge limits for that battery we used, and some other properties. And then these are some other constraints. For example, the catalyst light off, because you have in the exhaust, there is a components, the catalyst light off, that helps for emission. And the temperature of that one needs to be at the certain operating temperature. So we need to have a constraint for that one. You have a noise, vibration, harshness constraint. And actually, these constraints will become very important because if you don't include them, then you might not be in the optimal efficiency and you might report some good fuel consumption numbers. So it's important to have them over here. But the nice thing was, this provides a framework that I can use all the knowledge I have of the systems, and I know what are my constraints, and I put them in all to one optimization frameworks, and it's going to give me the optimal solution. So I'm showing here just the one slide of the sample results. So this is when here we have the engine torque, and here is the engine speed. And then this is showing for the UDDS drive cycle. This is for more air burn. And this is the highway drive cycle. And what you see here when it is a plug-in hybrid electric vehicle, and this was the mild hybrid. So what it was happening, it was choosing which modes HCCI to run, which modes RCCI, which mode SI, and another angle that is not showing here is how much was the EV electric vehicle was used over here. So when in that optimization framework, what it will doing real time, it will decide where would be the operating points that I want the engine to operate, and the engine was a multi-mode, and where to use the electric motor. The total energy saving for again, this would be the result would be dependent on the architecture we do. For the UDDS we saw when it's just a single mode RCCI was 9% saving compared to the state of the art that modern spark ignition engine that was used. When we had adding one more mode, HCCI was 3% more, and then finally when it's become fully multi-mode, it was 2%. And then for the highway, we saw numbers as you see here. It was giving us about 16-17%. So that can be changing when you are changing the architectures over here. We found that when we do it in the series, we found more energy saving compared to the power. So that was because, again, you want to have all the components to be as efficient as possible. So how about I know my components are fixed in hybrid electric vehicles and see what else I can do about here. So another piece of work that we look at it is that, again, that's all about the knowledge you have about your system. It is very common in the HEV control community and also, I would say also in industry. Then what we do, for example, when we look at the engine, is mostly use a map of engine. So a map of engine is more based on the static, what will happen here. So here you have engine torque, engine speed, and these regions will tell you which part is the best fuel, give you best minimum fuel consumption. But it doesn't tell you when I'm going from this point of the map to the other one, how much is the cost of changing from one mode to the other one. So those knowledge is missing. So what happens in the work we did, we said, okay, we are going to develop a dynamic model of the system that can see all those dynamics. And then we are going to incorporate those dynamics as part of our optimization. So we can make sure that we are going to catch those opportunities for energy saving. So this was the dynamic model that we experimentally validated. And finally, we showed the results. Here is just when you look at the IC engines dynamics parts, but then we did others for when you're having a clutch dynamics or other parts. So here we make sure SOC is the same, so when we can compare. What we found is that this is the fuel consumption. So when we have a dynamic model and when we study a state plan, we found there was about more than 8% difference in the fuel consumption. And then we said, okay, let's go just do a small change in our MPC. And what we did here, we include a term that is penalized some of those transients, saying that this fuel consumption, how much when you have a change of the engine speed and the change of the torque, you're going to have a penalty for that one. So he knows that if I'm going to go from one point to the other point, there's a fuel penalty associated with that one. And then we incorporated that result, and then we could see, okay, if I'm doing it that new controller, I could save 6% over here. So here there are more and more opportunities because for a lot of them, because of the simplicity that you want to have, you try to go with the static maps. But there's opportunity for dynamics that's happening. And then we do a lot of work with the OEMs. And then what is telling us is that they are now more willing to put the more capable control in the vehicles, because now the price of the processor is going down and the capability becoming more. So they are more interested to leverage many of these. So finally, the concluding part would be on the connected and automated vehicles. So again, we started from the engines, then we go hybrid electric vehicles. Now we are going to another framework that's the vehicles are becoming connected and automated. And so how many people are familiar with connected and automated vehicles here? Okay, so about 40%. It's good, almost 40%. And the peoples are changing. So when we talk with the people that we are working with in the industry, they say by 2021, all the vehicles that will be sold in US, they will be connected vehicles. What does that connectivity means? That information like a vehicle to vehicle, vehicle to infrastructure, so those are the information is coming. So again, controls, it's a great opportunity for the people that they do control of energy systems, because you got lots of this information. Now you have more predictability about your system, and then you can incorporate it here. I put some of them here. For example, if I know about traffic conditions, I know there is a road work over here, so I'm going to slow down. So there's no point for me to do acceleration and then do the deceleration. So when we arrived at Pearson Airport in Toronto, I was explaining these concepts to my wife, and we were driving, and there was a perfect example, because it becomes a traffic, and then it's become free, and then become a traffic. So if I know what's going to come next, I don't need to accelerate suddenly and then decelerate later, because again, for all those changes would be fuel consumption. So that's one. The other one is that for the traffic lights, that's another piece of information. It can tell you, because you know when you're going to pass, so there's no reason to speed up. The other one, information about the neighboring vehicles, like how much of their speed was their location. So you can tell them what would be my optimum trajectory of the speed, so then to looking at the safety. The other one for environmental conditions, because you know what is now and what is coming next, you can actually conditioning your powertrain such that you minimize the energy consumption. It's an area that we have been working on. The other one is about the route and topography. So you will know what would be the condition. For example, there would be a charging, discharging opportunities here for the battery. And then if you know it, you can incorporate that dynamics in your system and then do the control. And then some others is that where would be because you are connected, you know what is the next fuel or charge station availability. And I can imagine also then later on you will know, because the gas station, the fuel quality are different. So if I know what would be the variation of the quality, I can also use that connectivity data for modifying the control. These are some of the cases that it's a growing area, and so bring opportunity for further energy saving. So the work we are doing, this is a recently awarded work. It's about $3.5 million project, including Michigan Tech and General Motors. So what we have here, we are working on the 8 Chevy Volts. So we got 8 2017 Chevy Volts. And then what we are doing, very much similar to what I'm explaining. So we have a model, we are having experimental data collecting. So we are developing all those dynamic models. So we know for each components of the powertrain, how much is the energy consumption? How much of the vehicle dynamics as energy consumption? So we have those. And we also, this is the collaborative works, include the people from the civil engineering, traffic modeling, people from the electrical engineering, and the mechanical engineering. So we also have the information that we will tell us about the traffic, so we can optimize the vehicle velocity of these Chevy Volt to minimize the energy consumption. So here we have a V2V infrastructure to the vehicle. So what we have a Class 8 truck that we use it for research. This become our traffic center. So all the information of these vehicles goes here, and then that it can process the data, because especially for those traffic modeling, they need a lot of resources. And then they communicate with each of these vehicles, and then we can show how, for the different scenarios, how much would be the energy saved. And the nice thing about the Chevy Volt is that it can operate in all the modes we want. It can be an electric vehicle, it can be a hybrid electric vehicle, it can be mild, and it can be just the IC engine. So we can see for all different scenarios how much would be the optimum we can do here. Our target is about 20% when it's running in the plug-in hybrid electric vehicle or the HEV mode, and 6% when it's just electric vehicles, as we are working here. So these are the places based on the literature and some of the works we have done. So these are the promises we can see. When we do echo routing, is about by echo routing means that you know what's going to come in terms of the road grade. And so this is what we can see the range. When we are having MPC saying with the average of 10-20 seconds for different conditions, this was the range we can see for energy saving, and for the ICE and clutch dynamics, and this part for the electric motor and the battery inverter dynamics. These are the range we can see. By the end of the project, we have been about 6 months into the project. I think by the end of the 3 years, we can actually see how many of these lines are actually become, for our case, of the Chevy Volt that we have been doing. And this is showing the general structure. So what we have here, we will incorporate a model, a powered vehicle controller that it will tell me what is on real time, what is the route selection that we need to go that vehicle. The vehicle has 5 different modes. So we can say what would be the optimum mode that it can go, what would be the speed trajectory, what would be the IC engine motor torque speeds that we want to have here. So this will become kind of, at the end, will tell us these are the inputs and torque, engine, motor, and the brake that we will be using here. So on the bottom line, what it is, again, we are incorporating the knowledge of the dynamics of the system to try to use all the opportunity for the energy saving over here. This is the pictures of some of the vehicles. I think another one was on the chassis dyno, the vehicles we have. And this is the mobile lab, so students are working. So this would be the information from them, will be communicated here, and then we try to control. And then what we will have in the first stage, this is me testing with another engineer. What we will do, that the vehicle will tell them these are the modes to operate, and this is the vehicle velocity. So it will become a minimal change to the driver, to the systems. And later, if we see more and more promises, we might go down levels and then change all the control logics when we see more and more opportunity. But on the first level, when we are demonstrating, it will become very easy because the driver is mostly selecting the operating mode and the speed that it wants to go. And then later, we go for other levels. And so final slides for concluding remarks. So if you look at the Canada energy consumption, this is the portfolio. I look at it. For the transportation, is about 30%. This is 27%. This was based on the 2017, the data when I see on NRCan. And then if I'm looking at the energy for the greenhouse gas emissions, so transportation is about 24% and 12% of energy. So there's a lot of opportunity when we can save energy and at the same time reducing the greenhouse gas emission, because a lot of these sectors, they are using the fossil fuels, so then they can save energy. So to summarize what we talk about when we can incorporate the knowledge of the system dynamics to the control, then we can apply it for different energy systems. In the talk, we talk about the building systems, building to the power grid, advanced IC engine, hybrid electric vehicles, and connected system. And these are some of the results that we saw, except for this one, that this is more projected that we are working on here. And I would like to acknowledge the collaborator. As you noticed, the work was multidisciplinary. So these are the collaborator for the people, for the works that presented. Not, I have other collaborators not included here, but this is for the work that has been here. Included the faculty members from Michigan Tech and some outside Michigan Tech, UW-Madison, Berkeley, and University of Georgia, and then some from industry, Cummins Ford, and the CO3 IoT. And these are the collaborators in the next car project. And finally, these are the sponsors that have been helping us to let us continue this work. With that, I conclude, and thanks for listening to me.
Yes, I have a short question. When I talk.
So you made my job easier.
When you model, you have a model into the PV panels, right?
Sure, yeah.
But it didn't connect the PV to the grid. What's the concern with that?
Oh, in this work, we did it as a simulation framework. So what happens now, we built a Michigan Tech, we call it Sustainability House. So in that Sustainability House, we have been working with the utility. So what we are trying to do, because the grid needs to accept our power. So the work I presented here was simulation. But the works we are doing it now, we got in that Michigan Tech Sustainability House, so we got that PV panel. And then we are working with the utility, so then we can keep the power back to them. Because if you don't work with them, as you know, they're going to actually penalize you while you put the power back to the grid. So that's what we are working with them here. And so in that the same frameworks, we are actually got a one Ford vehicle, EV, so we have it in the same. So we can also use the battery of that Ford vehicle for some of the conditions, and the vehicle is available as energy storage.
Yeah, for the energy building, right? So the project, right?
Correct.
Yeah, so you have a very good control of the air conditioning systems in the buildings, right?
Sure.
So then you connect the PV, and you try to use the electricity to produce the PV, and you have an energy storage system. Then you connect the grid, right?
Correct.
So if you look at this bigger system, include the building, energy storage, PV, and grid, right? So then what kind of like a cost function you can consider? So,
Okay, so you're talking about this slide. So the optimization framework, so this is a paper published in the Applied Energy, so there's the details, I can pass it to you. So the control variable that we have in that optimization, so we have two cost functions. One of them is on the building side. So the building side was trying to, because we have done all different works. So some of them was more trying to reduce the electricity cost for the building. And that's on the building side, it was the electricity cost reduction, but at the same time trying to address what grid has been asking. What was it, for example, we don't want to violate the maximum feasibility load that we are allowed to have from the building side. And what was the ramp rate requested from the power grid? So those become, so that was on the building side. On the power grid side, so my colleagues in EE, what they were trying to see, which buildings should get the power, because they have a model, they were using the IEEE model for the power grid, so they can deciding how much would be the power going to the here, and they were doing different cost functions over there. Some of the works, it was based on the load factor, trying to make the load factor as possible. Some minimizing the losses in the system, so they can have the highest penetration that they have here. And so for us, we were doing it in MATLAB. For them, they were doing it in GAMS for the optimization. So these two communicate together. And the other works we did was that some of them trying to, how about to do it all centralized optimization, but then it becomes very expensive in terms of the computation. The others, what we did was that even it was how about become hierarchy. So we do on the engine, on the building side, and the other parts on the power grid over here. And so some of the variables will be decided. So how much would be the power from the grid to building? How much would be the power from the storage to building? And the PV, because we know, depending on situation, this is what we can get with the prediction. And how much of the grid power going to the storage. So these are the optimization framework. These are the variables that it will be decided here. Don't know if here, yeah, I think this one, yeah, 2017 one. So I think building to grid predictive power flow control for demand response and demand flexibility program. So there are some more details there, but this, again, one piece, because you can modify the cost function for it. Very good questions. Thank you. Yes, please. So what we have, the results you saw for the engine was the MPC implementation. So we actually implemented MPC. So that was working on the engine side. So it was using the MPC on the low-level controller for the engine side. So those ones were based on the actual implementations. On the electric motor side, so it has its own low-level controller. That's definitely saying implemented. But when I was showing the results of the energy management strategy, it was, and now we are using the models of this system and then trying it to head here. So that would be a work that we can doing it now, especially when we have it's saying that, okay, how much energy comes from the engines? Yeah. So that part was simulation. Yeah. Thank you. Good question. Thank you. Yes, please.
I have a question regarding, first of all, thank you for the presentation.
You're welcome.
Interesting. My question is about for hybrid electric vehicles. So we combine a spark ignition, for example, with electric motors. But how about if we combine spark ignition with the RCCI engine? Is it possible to do this in one single powertrain?
Sure, we did it, right?
Really?
Yeah.
No, in a real vehicle, I mean, not the test setup. Is it possible, or do we have any car running?
Oh, the cars are not running on the vehicle because it's become more research. But the things that we are showing here is based on the actual data. So when I was showing it the RCCI, those maps were based on all experimental data. So we have done mode switching between them as well.
Right.
So,
But do you think is it possible to do combine both of them in the like one vehicle or?
the only change that we did, because it's just the combustion regime is changing, so the only change that we needed, it was if I'm just going to do HCCI, even the change will become almost minimal. I'm just changing the control variables of the, say, cam timing. But when I was doing RCCI, HCCI, SI, the only change that it was adding here, we need one more injection of the port fuel injection. So that was the only change.
So
And actually,
combine
no.
all of them in one like engine.
It's the same engine.
Okay.
So then you can do action. And now, for example, we are working with Ford. So there are engines that they have two. One is PFI, port fuel injection, and DI. So and also Toyota has that type of engine. And because there are some benefits for a cold start and some other issues. So that platform when it's become available there, then it's become easier and easier. And, but typically, when we talk with people at OEM, because all these technologies are competing with each other, so at the end, the chief engineer needs to decide, should I invest here or there? That's a typical. At the end, it will go pretty much to the cost or interaction with them. So kind of control is helping it to make it more reality, whether it goes or not. I expect these modes, because it doesn't cost, as long as they are well calibrated, I don't see any problem then going to the engine. Especially if that operation is not changing much. The transient is minimized, yeah.
Thank you.
Yeah. Good question, thank you.
Questions?
Can I ask something quickly? I didn't understand if you have any collaboration in making the predictive model of the PV generation, or you just use the conventional?
We use the NREL model. So we use the NREL models that we have it for that part. So I would not say. Basically, we converted the NREL models in our MATLAB simulating for. So what we have here. So I would say there is no major novelty there, but we use the model from there and then we verify that. Helps me.
No more questions? Mahdi, thank you so much for your presentation. I would like to mention one thing in particular. Your presentation has brought back memories when our professors used to teach us that energy can neither be created nor destroyed. It can only be transformed from one form to the other, second law of thermodynamics. Thank you so much, sir. Enjoy.
Yeah, thank you. Thank you.